All right, guess it's going. So, kind of just want to walk through what I'm thinking as far as design. So, I've tested this little compression driver from B&C on, I guess, a few different um, horn profiles at this point. And the whole idea I've had with it is it's a really nice form factor for a Bluetooth speaker. Think like something similar to maybe a sound box or a JBL party box, but having really good pattern control and I guess probably bass extension down to 40 or 50, probably 50 is realistic. So keeping that in mind for form factor, probably looking at two 6.5-inch woofers with some kind of horn. My initial idea was that that horn would be on the top, and then the woofers below it, something like these. But after kind of testing that out a bit, I was thinking, well, I could actually probably make it smaller because I want to make the horn as large as I can realistically, to get good pattern control. But the bigger you make the horn, the bigger the box is going to be, especially if you have to put two woofers below it. So the original idea was kind of, I'll pull this over here, taking two of these little 6 NDL 38s and building a box around them. So that's a pretty compact form factor. And this is the horn that I 3D printed yesterday, which does perform really well. Um, there is an opportunity too to because the woofers are taking up so much space down here, widen that out a bit, which means we can probably get a little bit better of a horizontal pattern out of it. And there's of course plenty of room in the back too if we need to extend that out any. But then the idea was like, all right, um, what if you made the whole aspect ratio of this box instead of being kind of tall, just like really wide? So that kind of keys into this idea of doing like a multiple entry horn arrangement, which would it really technically be one that benefits from all the aspects of that in this small of a size? Not really. The main kind of appeal of a multiple entry horn is you get that point source summation. So it does seem like all the sounds coming all from one place. And to do that, there's like a lot of little variables you have to account for, like placement and size of the taps and how big the horn is and the flare rate. And once you get all that right, then you actually get that kind of wow effect when you're listening. But at this scale, it's kind of hard to get that. But what you do get is if you take these woofers, and put them further up and tap them into the side of this horn, just imagine that horn's a lot bigger. Well, suddenly the box can be way smaller and basically just be kind of that, which is the appeal. So, like, yeah, you're kind of like not really getting all the benefits of it, but it's more about saving space because if you can kind of make this work, um, and design the taps in a way that don't interfere too much with what's going on with this horn, then you essentially have like a something like a 12-inch by 6-inch by maybe 10-inch box, um, that's going to be super compact and high output. So in ABEC, and that was that script I was pulling up, um, the horn profile kind of looks like this. So this is like iteration 7, 8, 9. I lost track. Um, but it's not terribly complicated. I tried to keep the actual flare rate matched up to what it should be for a multiple entry horn, um, because the rate at which that expands should follow like a certain kind of rate. So every distance that you go um, out of the mouth of the horn, the side walls and top and bottom walls need to expand. So tried to get that kind of close, but I didn't want to do, like try to really make it like a straight conical horn too much because then we lose out on a lot of the really good pattern control we'd get with a horn like this. But this does measure 12 inches wide or about 32 centimeters. It's got these little bumps in the bottom, which I think, if my understanding of ATH is correct, is as you're adjusting the parameters to get a certain vertical coverage pattern, it will actually increase this kind of path length along this wall by adding these bumps, which can get you a little bit better pattern control. And for this one, which did just finish baking in the sim, it does look really good. So here's the horizontal, and this is scaled from, I think, 800. Yeah, 800 to 20,000 because it really wouldn't be doing much below 800. Up to uh, out to 180 degrees, so fully wrapped around the box. And if you kind of mouse over where the -6 dB point is, it's like, yeah, 45 degrees ish. And I'm pretty happy with that shape too, because that's definitely like constant directivity throughout the operating bandwidth here. I might sim again just down lower to lower frequencies too, just to see what the horn does, but I imagine that you're going to see it becoming pretty omni at about maybe 700, so it really wouldn't matter that much. Vertical isn't quite as clean, but it's still pretty good. There's a little bit more narrowing up in the top end than I'd like, but it's really not bad, and I think having a pretty narrow vertical is fine. Um, I think this would be, yeah, like 60 degrees, you could call it. Maybe a little less, maybe a little more. I mean, it varies, but I'd feel comfortable saying this would be 60 degrees just based on where that slider is. But I guess what I'm going to try now is actually getting this mesh file into Fusion, which is usually a challenge and it's going to be messy, but um, that's going to be like the next step into actually printing a physical prototype of this. So we're just going to go into Ath and actually change these parameters. So I don't need a mesh enclosure. Change that in, well, actually that shouldn't matter. And right now I'm just going to tweak these settings to get me a good enough quality mesh file. Oops. Now, what I'm not sure of is if I import these slices into Fusion, if it's going to do the back of the horn, because I really don't want it to. I'm going to find out. Um, that's the wrong add-in. Might be surface import. Here we go. Okay, that's something. I guess that's right. Just need to actually scale it because for whatever reason it brings it in at a way too big. I think it's 0.1. Whoops. Looks about right. Well, it's not going to want me to measure that. Yeah. So I need to make this solid. So I think in order to do that, I probably want to swap the normals. And then I'm going to hide all this other stuff I'm not using anymore. I think it's thicken. Let's see if that works. Nope, it didn't like that. I think that should have been -3. Yeah. Okay, there we go. And that's like probably thick enough. It's just a prototype, so I'm not really too worried about it getting broken. Cool. So now I just want to like visualize where we're at with the woofers if they actually tap in on the sides. And they should be set up for 90°. Something like that. I think it's going to be a lot of 3D printer material. And I might not even have these at a 90° angle. They might look better tilted in maybe a little bit. So in an extra 5. No, that's not going to be happy with me today. Again, this is very rough, so it doesn't need to be perfect. Yeah, maybe something like that. But I think size-wise, it looks pretty good. Um, I may even move them back a little bit. I'm just going to add the mounting flange for the compression driver to see kind of where that would sit and then how far we can shove these back. Because the further back we can get them, not only does that mean we get a better tap location, but also we'll be able to make the box fit a little bit tighter. But I totally guessed that that was going to fit in a 12-inch wide box, and it looks like it did. So that's cool. And for whatever reason, I don't think that's a flat surface. No, so we need to make it a flat surface. This is a very crude way of doing this, but it works. I need to pull up the drawing. Okay, so bolt hole diameter is 53. I think first I need to actually figure out where center is. Approximately, because it's not going to be perfect. Let's see how close that is. Cool. All right, and that is a M5 hole. Let me see what I put in the other one. Okay, 5.5 diameter. And now I just need to build like a flange that's going to be wide enough. So I'll probably just have a circle come out that size. I'm going to reference this again. And that's roughly right. And then maybe some kind of rectangle here. Like that. And I can kind of round that a little bit. Yeah, I think that's too wide. All right, I'm gonna have to figure out what diameter that circle is on the other one. Okay, we've got an inner at 25.4, outer at 35. Actually, I think that needs to be this one. Okay, try that again. Cool. I have noticed when you import stuff from Ath, it does make Fusion pretty slow. All right, so that should match up where the compression driver will sit, which does show that we have some room to move those drivers in a little closer. There's probably like an optimal place where these don't collide with the edge of the horn as much, but at this point I'm just trying to figure out how much space this is all going to occupy. And I think, all right, so we're going to assume this has 1,000 Hz crossover from compression drivers, which means our tap needs to be a quarter wavelength from 1,000 Hz, which is, I think, 85 centimeters. Yeah. Yeah, 1,000 Hz wavelength, 343 millimeters. So, yeah, 85 millimeters. Drawing a sketch to make those holes onto here, though, might be a little tricky since that's not really a flat surface. I mean, I can try to like approximate it. It's not like it needs to be exactly 85 millimeters. That's the maximum. So if we kind of just think about our compression driver exit being 25.5, that angle, well, is roughly, let's say like 125. Cool. Yep. So what I can do is take a sketch over here. There's also the question of, do I do 2 taps or 4? And I think the answer is 4, because if I were to do 2 taps, just kind of like on the sidewall here, let's just imagine that. Um, that's kind of in the middle of like a flat area of where the compression driver is going to be firing. And it's generally better to put them more towards the corners. And not only that, we can probably get more area if we do 2 smaller ones versus 1 large tap. And I guess the last thing is it's more even with how the cone works. So if you think about the cone here, and um, if it has just one single exit, then you have a different time of arrival from like the edge of the cone over here to that exit, and the edge of the cone over here, the edge of the cone over here, versus like in the middle. But if you do 2, then yeah, you have a more even time of exit out of that tap from different areas of the cone. And I will need to actually calculate the size of that. I think before I go any further, I probably want to. Oh, that's cool. I probably want to like verify this in horn response, just because there's a lot of things to check as far as this arrangement and making sure that it'll actually work. So we'll go ahead and do that. I might need to do a new record. All right. Drivers we're working with today. I'm going to use the 6 NDL38. So we've got those. I'm just going to sim it in like um, a bass reflex box. I know that like, Horn Response has the multiple entry horn wizard, which I use, but at this stage in the design, I find it faster to establish some things just with the standard bass reflex and some changing some settings. So how do you do this again? Design, bass reflex. All right. And rather than figuring out these values painstakingly, because I hate doing that in horn response, we're just going to get them out of WinISD. And I tried a bunch of 6-inch drivers for this, and the 6NDL38 just came out on top for the 50 hertz tuning and the size of the box. I guess technically it's more of a mid-bass driver, but it just sims really well for this. I think with full input power, it's like 180 watts, and it's putting out 111 decibels at 50 hertz for two, and it's not even like a lot of air velocity out of the port either. So the air velocity looks good. The cone excursion, I mean, that's right at its limit for that amount, but and then a 44 hertz high pass filter. So that that seems to be a really good combo for this box. So I'm just gonna try to make this build around those. But what I actually needed to get here was the box information. So we were doing 30,000 square centimeters. I think that just might be 30 liters in horn response. Yeah, 30-liter chamber. Chamber length doesn't matter too much. We'll say 25. That needs to be ports. So port cross section area. I think I'm going to do 2 square ports and have them come off of either side. So one port on the left side of the horn, one port on the right side of the horn. They should be operating at low enough frequencies where that's not an issue. I don't want to try to tap them into the horn because that's a massive headache and more trouble than it's worth. So we'll simulate 2 rectangular ports that work for this. I just want to get those values right first. That'll be like 35 by 250. Well, I need to actually see what that height is. 180. Okay. So the height is 180. Yeah, probably 25 millimeters, which is kind of small. Like that aspect ratio is a little like longer than I like, so maybe we can force it to be like more chopped off. So like instead of having the ports run rectangular all the way up and down the side, we could probably do like more towards the middle. So ports right here and here. Well, but then I might run into the woofer. I guess I could do 4. Yeah, let's see what 4 looks like. 4 square-ish ports. Forty by 40 looks pretty good. Check our air velocity. That's pretty good. That's a full output. That's probably audible, but I guess I could go like 45. Yeah, that's better. All right. Well, the main thing I needed to get in here anyways was the length and the cross area. So 25 and 72. Can't remember if that's per port. We'll find out. All right, 25.23, and the port area is 72. Cool. Don't think I need these yet. Yeah, and we'll just zero out all the horn stuff since we're just doing a regular box. All right, check the model. So this is always a good idea in horn response just to make sure everything looks right here. So you have your driver diaphragm in the red facing out, your box represented by this area, and then your port, which looks about right. It doesn't look like overly long and skinny or weird shaped. So yeah, I think it passes the visual test. Okay, we'll check power. That's about what I expected, yeah. I do think that's for one driver though. So I do need to fix that. Try that again. There we go. Okay. Yeah, this is what I'm expecting to see. So we have our low knee at about, I guess, 45, which is a little bit lower than what when ISD puts it, but it all just depends on what simulator you're using. You can get values all around that. Uh, looks good. Make sure port velocity isn't ridiculous. Yeah, I think this is all pretty good. So what I wanted to check now though, because like we know that's pretty easy. That's just two drivers in the ported box. But need to see what effect adding like a front chamber would have, because if you think about the way these are going to be positioned, they're going to have an enclosed area of air that's trapped like where the cone is, and then an exit, which is a certain diameter, which we haven't established yet. We don't know what size that exit's going to be yet. We can figure out what size kind of that displaced area is. And because we're 3D printing this, we have some flexibility to make that larger or smaller. And the effect of doing that, so imagine like creating more space, um, in front of the cone. Um, you're going to basically shift. Oops, I pull that up again. Yeah, if you add more area under the cone, this knee on the high end, which is at 1,000 right now, is going to be brought down in frequency, which can be useful depending on what you're designing. If you take um, area out of that, so like you use a cone filler, they're not phase plugs in a multiple entry horn. They are a cone filler that you use for decreasing air trapped. Um, that will extend the upper response knee. But in just a direct radiating box like this, like just the regular ported, um, that knee is about where we need it. So I'm really curious to see like what adding that chamber is going to do. So throat chamber volume, that's going to be on the spec sheet. So what we can do is find out from the manufacturer. Yeah, where is it? Yeah, air volume displaced at Xmax. So that's an approximation of how much air there is under the cone. It's not going to be very accurate. but it gets us kind of close, so we can just try a few different values around that and see what it does. The better way to do it would be to actually model the full cone. Um, I don't have these drivers on hand, so we're just going to have to make some assumptions around how much air is displaced under here. So that's cubic centimeters. It said 79. And then I believe the ATC is the size of the tap hole in at least in the context of what we're doing. I mean, what is this circle? 70. It's probably about right. Oh, I forgot. You have to actually double these. Um, yeah, we'll see what that does. Okay, I didn't plug in the values right. What I'm expecting to see here. Oh, hang on. Well, I guess I could just answer on stream too, but um, yeah. So somebody had asked, what is Ath? What does it bring? The great part about Ath is it's script based, like a script based horn and waveguide designer. So basically, you can tell it like the parameters of your design, things like the size of it, what you want your coverage angle to be. And you have like a few values to tweak that's going to like basically morph the shape of it. And then it spits out like a 3D model directly into ABEC for simulating. So it's a good bit faster than like modeling every single horn profile from scratch. So it's just like a really, I mean, once you get the script set up, you can have it generate the mesh in like seconds, and then you open ABEC and it pulls it right in. And I can show too, like if I wanted to make one of these values like crazy, rerun the script, let it do its thing, it just recalculated the whole profile. And then of course you can run it and then simulate it, which can take anywhere from a few seconds to a few hours, depending on how much you want to simulate. But I mean, at this point in the design stage, I just use WinISD and horn response because it's just faster, honestly. Eventually, I'll get everything modeled in Acrobat and do all that, but that's a bit more involved. Let's see. I might have to go to an old design to figure out how I did this in the past. Yeah, I might actually just need to use the multiple entry horn wizard. All right, I'm gonna get all that set up. I'm gonna pull up a reference image for this. All right, so first record. Okay, first record is going to have the tap area, so we're going to do 70. And then that needs to be whoops, the thickness of that wall, whatever that's going to be. We're just going to say we're going to say that's a 6 mm wall. All right, and that's got the correct driver specs in it. 30 liters, that's fine. That's fine. Yeah, it did have the wrong value in here. Okay, it actually tells me that value, so 3023. I'm assuming that's for both drivers. Oh yeah, it does send the model directly to Acrobac. Well, Ath, but you can get it into Acrobac pretty easy once you have it in Ath. Or sorry, ABAC. Yeah, we're just gonna assume that's right. That number still seems low, but we'll leave it there as is. All right, so that's our first record. Um, this needs to be ME1, which is gonna mess up all my values. Lovely. Could also just do this. Ah, I remember what ATC was. I got it mixed up with AP1. All right, 25 liters, or 30 liters, 25 centimeters. Um, 72 by 25. All right, what were these again? 3023, 170. All right, activate. Now we do a new record. That is just a normal ND. And these are actually where the horn profiles are going to go, which again doesn't really matter that much in the context of the compression driver because we already have simmed that with ABAC. but it will affect to some degree what's coming out of the 6-inch drivers. So we're going to use another tool to approximate those values. This is the Synergy Calc spreadsheet, which is really useful if you ever want to design one of these. And I'm just going to plug in some old values or some rough values here. That's fine. That's probably fine. Uh, Pattern control, like this variable, is the one thing you control in the spreadsheet that's going to affect the size of the horn. The lower the frequency you want it to hold pattern, the bigger the horn's going to be. I won't, because I'm trying to approximate what I've already got a model of, I want it to be 12 inches wide. Right now it's 30, so I'm going to try 700, maybe 750. Close enough. And then double checking, I mean, that doesn't matter. Yeah. Yeah, now we have our values for horn response for this screen. Uh, Maybe? Oh, that's right. And a lot of people get like confused by this part of horn response, which it is confusing and needlessly confusing. These variables, all these S's and cons and L's, is just telling the program like the actual, it's telling it a 2D representation of your horn. So the best way to think about it is, I mean, for a multiple entry horn, S1 is like way down there, S2 is in the middle there, and S3 and S4 and 5 actually are further out. But it's just a cross section saying that like if you were to slice the horn here, it would be this many square centimeters. If you were to slice it here, it'd be this many square centimeters. And then the values that are actually over here on this column are saying how far to the next slice. So you can make just about any profile with these, and then depending on what this value is, that's going to tell you whether it's like a conical flare or exponential or parabolic or whatever. Let's see if that's everything though. No, we need to put some values in that's going to make it happy for simulating a compression driver, which are not going to be right at all, but we don't really care too much. It's going to be 2. Oops, did I miss S5? There is no S5. Why is it asking for an S5? Oh, I think that needs to be 0. Yep, okay. Yep, this program's very annoying. right, double check all the values. And save. That one's activated. So horn response knows that whenever you run the multiple entry horn wizard, because it uses two separate records, it's going to look for whichever one's activated. And I'm fully expecting for this to be completely wrong. Okay. That doesn't look quite right. Let's see. That might actually be right though. So I think that's supposed to be the rear of the box. That's supposed to be the volume of air that's trapped between the cone and the horn wall. And then that's the tap. That volume looks too high just based on this diagram. Chamber 2. Okay. Oh, I mean, that looks better. Yeah, I think we have some, well, no, actually, that's not terrible. Still, that's interesting. So we do get the correct kind of low knee there, which we'd expect given our like simple bass reflex simulation, which is good. Um, this all up here though is a little bit more confusing. So offset rear output is just going to be from the port. So that's just going to be like where the port's most effective, which is around its tuning frequency. And then we see that taper off. And then the horn mouth output is what's going to be actually for coming out of the front of the horn. I guess what I could do here, because I don't really care about simulating a compression driver for this, like it's kind of irrelevant. I guess what I'll do is probably set its voltage to 0. Oh, okay. Or close to 0 to see if we can get just the 6-inch drivers modeled. Yeah, it's the same response. It's really hard to tell where that knee is. So if we remember the first sim we did, it had a roll off at 1,000, but now it seems that tapping it into the horn has created a phase inversion there and a few peaks, but it's not really telling us a whole lot, which is making me think our model or the data we put into horn response might be wrong. I'm going to go double check these numbers again. That does seem really high. I'm curious what that does. I think what it might be doing here is making that chamber too long. So if you think about our model again, if you were to take these drivers and if you had to, for whatever reason, move them back like this, which sometimes you have to because there's no space if you're using like small mids, that means you need to create a kind of long path to actually get to the horn. And when you do that, people usually get that kind of um, really big null, which seems to be what's showing up. So definitely have something wrong set up in the measurement or in the model because that distance there should be like, yeah, like 6 centimeters or millimeters, not centimeters. Ah, that might be it. I probably have the units wrong. So that's going to be, it should be 6 actually. Oh, that's centimeters. Yeah, cool. I think I think that's right. This is what happens when you constantly work in inch and metric. Schematic 2. Okay, that's better. So this is the tap right here, and now that's showing the correct like 6 millimeters. So it was showing 6 millimeters, which would have been like a really long tube, and hopefully that fixes our issue. It's better, slightly better, but I still think that let's see. I still think that this length is also too long, which it's not ATC, is it? Let's see. Oops. No, it's not ATC. I think that was 170. Maybe it's LRC. Nope. That was 25. I wish it actually showed you what these values were in the screen and you didn't have to go back to here. All right. So the rear chamber's good. I'm happy with the volume and the distance to the back wall. The ports are good. Wait, I think I might have found the issue. Ah, yeah. These should not be. These are for the compression driver, so that would explain. Although that shouldn't really matter too much, but we'll see. So that's 170. All right, try that again. Okay, there we go. Now the model actually looks correct. So we're actually getting somewhere. There we go. Okay, that's what I wanted to find. All right, what we're doing is this area right here corresponds to this gap here. And we need to get the width roughly to what the driver diaphragm surface is, maybe a little bit wider. Yeah, something like that. Because we don't want the cone to be firing too far to that exit. We want it to be pretty close. And now that just visually again looks like the volume might be a little high, but we'll cross that road when we get to it. Oops. Actually have to get back into this. Okay, cool. That's what I wanted to see. Awesome. So what we're looking at here is on the low end, that's going to be output from the port, which I can show. Well, I thought I could. Oh, yeah. So that's output from the port on the lows. That's output from the horn mouth. Combine them together, you get this. With multiple entry horns, depending on the size of the horn and the flare rate, you're going to get this peak here. The top of the peak, this is what I was referring to either earlier, is going to represent like where your high frequency falls off like a rock. And if I remember correctly, the way you can manipulate where that is by changing the volume of air under the cone, which we would need that to be like 1,000. I mean, the compression driver, like my goal with the horn is to get it down to 1,000 anyways. So we'll see if we can tweak these values to get that peak shifted up a little bit, which shouldn't be a problem. Let me make sure I got the right value to tweak for that. It's going to be easier if I go to the diagram. Yep. Okay, it's VTC. So now I can go back to total power. Cool. So adding volume shows the curve going down. Removing volume puts our curve further up. And we need it to be, okay, cool, that doesn't affect anything. Here. Yeah, that's pretty good. So it's good to know that we can actually get these drivers to 1,000 hertz, and that's a pretty flat looking curve, all things considered. I mean, we start at 90, we peak at like 96. You probably add like a second order filter at 650, and then you have a really nice roll off to match whatever slope you're going to meet for your compression driver. So let's save that. So our throat chamber volume in cubic centimeters is 218. Now the hard part, that number needs to be translated into 3D space into the actual model. So whatever complex geometry is needed to mate this driver up to this horn, there's going to need to be about 218 cubic centimeters of air to get that ideal response. And I imagine this is all going to have to be 3D printed. So given its width, probably slice it in half, like here, and then just print one half at a time. Yeah, I do think before I do that, I'm going to actually print this horn out without the taps. Well, yeah, I'm going to print this horn out without the taps just to measure it and test it. Um, see how it does, see if it actually matches the simulations, which again look really good. So if we get anything even close to this, that's a really good horn profile. Um, and then from there, actually design those kind of mounting point chambers, whatever you want to call them, for the 6 inches. Let's see. Probably the easiest way to slice this. Yeah, it looks pretty good. And I imagine I'm probably going to have to do like some kind of flange just for now so I can actually mate the two halves together. Probably going to use like epoxy. And also now that I look at it, I really don't like that slice um, down the middle of that hole there. So this might be like a 3-part thing. So I could probably do sliced here, and then like maybe here. I'm gonna hide that last sketch. Yeah, so that part would get epoxied on after you have the two halves of the horn together. See if we can actually make that happen. The first slice I want to do is this one. Oh, well, that's not even remotely right. Maybe it is. Yeah, no. It should slice through it. Maybe I'm misremembering how the slicing tool works. Let me actually try turning this into a body, see if that does anything. Oh, okay. Yeah, that's more or less it. All right. The amount of disorganization in this file is pretty accurate for how my prototypes go. So my thought here is to make some kind of flange. So like just extend this out a bit so that we have a little bit more area for the epoxy to grab onto when the two sides go together. And the easiest way to do that is probably just this. Maybe. Yeah, not that. Just gonna do both sides. I only want to take this one. Oh, there we go. Yeah, like an extra 3 millimeters. Doesn't need to be a whole lot. Not a fan of that gap. I wonder if there's like an easy way to loft that. Yeah, that's not going to be it. I don't think this works around curves, does it? Yeah, no. I don't really want to have to resort to using forms for this, but will if I have to. Yeah, let's try extruding it and seeing if there's anything we can do after it's extruded. Because like that's all fine up here. I can even like do that. Oh, well, I would say that's good enough for a prototype. Yeah, it's not gonna let me delete you, is it? Nope. I mean, since it's getting 3D printed, that should just stick anyways. I'm not too worried about it. Don't know if there's a quick way to mirror that down here. So I'll just repeat what I did. Actually, I could just do this. I think that works. Yep. Oh, no. It's possible that was actually worse. All right. Also realize that the info that's been at the top of the screen has been wrong. All right, so edit, get rid of that. Okay, it likes 2.99, but not 3. Cool. Looks pretty good. The other half should be a direct mirror, so I don't need to do all that again. I do want to check the throat adapter. I mean, I'm imagining putting like epoxy on here, and that should really be enough to hold it for a prototype. But yeah, that should be enough. It's not a very heavy driver. All right, I think this is just about ready. Yeah, all right. Now we can actually pull these into Prusa. That should be really easy to print. Cool. And now the actual horn shell, which is a little bit more complicated. So I learned during the last print that printing like this isn't necessarily a great idea because of the overhangs here. So even with supports underneath, this still kind of ends up being a little stringy. Like it doesn't, I don't think it affects anything acoustically, but it doesn't look good. So I think it's actually a better idea to print um, like this, which means yes, technically it's a longer print time because you have more supports, but it ends up better looking. Actually, that's going to be a lot of supports, but it is what it is. So 40%. I want to do variable layer height too. The reason why is because when you have these vertical sections down here, um, the layer lines look fine, but as you move up to here, they get kind of coarse, and again, they just don't look very good. So actually showing you this before doing the, well, let's turn that off. Yeah, you can kind of see like where the infill layers are beneath. So that's where I like to use this, which I don't really know why it's not showing up like it should. Oh, there we go. So I'm just increasing the detail of the layers here. Cool. And where are supports? Yeah, we'll just leave it on default for now. Enzo Galen commented, and on the split side. I might have missed that. What was that in context with? Yeah, so now we have much smoother layer lines at the top, so that should actually end up looking really good up here. I probably don't need as much. Oh, to print on the splitted side. Oh yeah, the problem is my 3D printer just isn't big enough for that. I think that would be ideal, actually, if it was big enough, but I think it overhangs. Wait, does it not? Maybe that does actually work. Oh yeah, good point. I'm gonna reslice that. Uh, let's see. That's at 1 day, 11 hours. That's a long print. I think I can probably get away with being a little bit more aggressive on supports. So we'll see what 30 looks like. See if that gets any kind of improvement in print time. And that's just 1 day. That's not bad, but you do raise a good point. Like, I could just sand it since it's a prototype and it doesn't have to look pretty. Um, let's see how much faster that is. And I need to reset that. Add the detail on the bottom now. It isn't exactly like the most intuitive to use. That's probably about good. Yeah, if this is like significantly faster, I might just do this and be okay with it looking ugly. 13 hours. Yeah, I'd say that counts. I don't like these supports in the middle. Don't think they're needed. Okay, that's a problem. Wonder why it's doing that. Just trying to do an overhang perimeter. I've had this issue before, but I forgot how I fixed it. But for whatever reason, it's like it's splitting the model. Um, and it might be something that you can just fix by tweaking these. me just try changing that value and see what that does. Yeah, because it's like, for whatever reason, modeling these empty layers, which if I go to the actual 3D model, there are no empty layers. But then you go to the slicer and they show up. Yeah, empty layer. Faulty model. What happens if we add detail up here? I mean, past this, I can just try re-exporting it because I almost am certain it's because of this part in Fusion, because that's like a really small gap and it's just confusing the slicer. But I want to see if we can fix it in here real quick. I mean, maybe? Nope. The error went away. And it's a 12-hour print time. Okay, we got infill, infill, infill. Cool. Yeah, seems to have fixed it. So there's just going to be a little bit of roughness down here wherever these supports touch the model, but I guess that's why I got to sand. I'm going to double check to see if there's anything else we can shave off of here. Let's see if grid's faster. Okay, it's doing that again now. That's fun. It's not really any faster though. I don't know, 12 hours, 25 minutes. It's pretty fast. 167 grams. I might just send it, see where this comes out. And yeah, I'll probably end the stream there. Um, Once I actually get to testing this, I might try the stream again, or inevitably when I have to design the part where these go into the horn, because that's going to be a pretty big challenge. But yeah, I'm gonna call it there.